Good morning, dear students. Today we'll start with the second instrumentation, that is colorimetric estimation of an copper. So, in this colorimetric estimation, colorimetric estimation of copper depends upon the principle. The principle is that when monochromatic light of intensity I naught is incident on a transparent medium, a part of the light is absorbed by the medium and the part of the light is reflected, that is IA and IR, and the remaining part of the light is transmitted. So a monochromatic light, if it falls on an absorbing medium, part of the light is getting absorbed, part of the light is getting reflected, and part of the light is getting transmitted. So intensity I naught is equal to IA plus IR plus IT. So for a glass air interface, it is negligible. IR is negligible. So I naught, intensity of incident radiation, is equal to IA, intensity of absorbed radiation plus intensity of transmitted radiation. Now colorimetric principle is based on the theory is based on the two laws, that is Beer's law as well as Lambert's law. Now, what is the statement of a Beer's law? The Beer's law states that absorbance of a monochromatic light is directly proportional to the concentration of the absorbing medium. So, absorbance is directly proportional to intensity of the light which is getting absorbed by the medium is directly proportional to the concentration of any absorbing species present in that medium. And Lambert's law states that intensity of monochromatic light uh, absorbed by an absorbing medium is directly proportional to the thickness of the absorbing medium. So this thickness is also referred as the path length of the absorbing medium, or the length by which the light travels. So put together, Lambert's law states that the absorbance of a monochromatic light is directly proportional to the concentration and the thickness of the absorbing medium. So absorbance of any monochromatic light is directly proportional to the concentration and the thickness of the absorbing medium. So IT by I naught is equal to epsilon C into T. That's equal to a transmittance T. Epsilon is the molar absorptivity, C is the concentration of the species present in the absorbing medium, T is the thickness of the absorbing medium. Now, T is called as the transmittance of the light absorbing in the medium, and if you multiply with 100, that is becomes percentage of transmittance. And if you inverse the ratio, that is and taking logarithm on the both side, so log of I naught by IT is equal to epsilon C into T. That's equal to a 1 by T, capital T. That's equal to nothing but A, where A is the absorbance of the medium, where epsilon is the molar extension coefficient, T is the path length of the, or length by which the light has traveled, and C is the concentration. The concentration usually expressed in moles per liter of the absorbing medium. Now, for a given substance, this epsilon, that is molar coefficient of absorption, is constant at a given wavelength and also a fixed path length. And A is the absorbance, that is usually measured in optical density. Now, in the principle of estimation of copper, a series of standard solutions of copper sulfate is prepared. So the source of copper is copper sulfate solution, and the test solution is added with ammonia to get a blue tetraammonium copper 2 complex. Normally copper ions are made to react with ammonia to convert into a complex. That complex is nothing but tetraammonium copper 2 sulfate. tetrammonium copper 2 sulfate and is diluted to a definite volume. And absorbance of each of the solution and the test solution is measured at a wavelength of 610 nanometer. Since this complex absorbs maximum absorption is found around this 610 nanometer, and absorbance values are plotted against the concentration of copper to get the calibration curve, and the concentration of the test sample is determined from the graph. Now, how the procedure of performing. So, in a series of volumetric flask with a 50 ml capacity, added with 5, 10, 15, 20 and 25 ml of copper sulfate solution from the burette, and to each of the volumetric flask added with exact quantity of 10 ml of ammonia solution from the burette, and shaken well, and the volumetric flask is diluted up to the mark with distilled water and shaken well. The blank solution is prepared by adding 10 ml of ammonia to one of the volumetric flasks separately and diluted to 50 ml, and the test solution is prepared as said above, and test solution whose concentration of copper to be prepared is also prepared according to the same method and whose absorbance is noted. Now the blank solution is taken in the first step in an cuvette. Cuvette is a small test tube kind of apparatus. In the 3 by 4th of the volume of the cuvette is taken first solution, that is 5 ml, which is added to first volumetric flask and diluted to 50 ml and placed in a photoelectric colorimeter. Now, zero absorbance at 600 or 610 nanometer is obtained by adjusting variable diaphragm or pressing zero absorbance button and placing the blank solution. The absorbance of each of the standard solution and also the test solution is measured. Now, a series of solution which we have prepared 5 different volumes starting from 5 ml to 25 ml. Each of the solution whose optical density, that is absorbance, is measured with the help of a photoelectric colorimeter, and the test solution absorbance is also measured. Now the graph is plotted with the concentration of copper on the x-axis and in the y-axis. Now instrumentation consists of source is a tungsten bulb. Tungsten bulb is used as a light source. Filter is a device for isolating monochromatic light. In between, after the source, a filter is placed to isolate the monochromatic light. Sample is to hold in a glass cell. Glass cell is commonly called as a cuvette. And photocell which converts the emitted light, that is from the cuvette into an electrical signal, and which will give you as an absorbance. Now when you look into this figure, S is the source and the radiation is passed through a filter, and the filter role is to isolate the monochromatic light passing from the source. And once this source filter gets isolated with the monochromatic light, that monochromatic light is made to impinge on an test tube containing, that is cuvette containing the complex ion, and the light get transmitted. Part of the light is get absorbed and the part of the light is get transmitted, and the light, when it impinges on the photo cell, so that this photo cell converts into an electric signal with the help of a recorder, and it is displayed on the screen as an optical density. Now the graph of optical density, that is observed optical density from the various solutions using a 5, 10, 15, 20, 25 ml of copper sulfate in each of the volumetric flask is noted, and graph is plotted with the observed optical density against the concentration of copper 2 plus ions. Now graph is a straight line which will pass through the origin. So this is the calibration graph. Now the same procedure is repeated for the test solution, and whose optical density is also measured. Now from the test solution, let us say this is the optical density of the test solution whose concentration of copper to be determined, and plot a straight line which will intersect the calibration curve, and that straight line you extend it to the x-axis, and here you find out the concentration of the test solution. So concentration of the test solution usually expressed in milligram per liter or in ppm. Now the result is concentration of copper 2 plus present in a test solution from the graph, that is milligram per liter. Now the reactions. What is the reaction is that copper 2 plus is the source for forming the complex, and this copper 2 plus reacts with 4 moles of ammonia, which is fixed moles of ammonia 10 cc in each of the volumetric flask which is being added, and this copper 2 plus reacts with 4 moles of ammonia and it forms a complex ion, and this complex is deep blue in color. This complex name is tetraammonium, 4 moles of 4 ammonium tetraammonium copper, which is oxidation state is 2, so tetraammonium copper 2 sulfate, and it's a deep blue color complex which has a definite absorptivity at 610 nanometer. Now observations and calculation is very simple. From the graph, from the absorbance of the test solution, concentration of copper sulfate is measured in ppm, milligram per dm cube. Now this is the tabular column which you have to do it during the course of finding out the concentration of copper by colorimetric method. Now the different volumetric flask, flask number 1, 2, 3, 4, 5, and 6 is the test solution. Volume of copper sulfate solution in ml, that is X. You add 5 cc, 10 cc, 15 cc, 20 cc, 25 cc, so on. And each of the volumetric flask is also added with fixed volume of the ammonia to form the complex tetraammonium copper 2 sulfate. So 10 cc is added to all the test tube, and concentration of copper 2 plus is found out with the help of simple equation. X into V. V is the total volume, X is 5, 10, 15, 20, 25, so on, into 63.54. This 63.54 is the atomic weight of copper, divided by 50. So you will get the concentration of copper, and optical density or absorbance is noted for all the 5 volumetric flask, and the test solution is prepared according to the same method, and from the absorbance of test solution, absorbance is also noted. From the absorbance of the test solution, a line is plotted, line is drawn intersecting the calibration curve, and from the calibration curve it is extended to the x-axis to get the concentration of copper 2 plus ions. Thank you.